Hello, I'm John Linz, and in this video I'll be discussing the momentum optimizer and how to apply it to gradient descent to not only converge faster, but also to converge at a more optimal local minimum in the loss function. To preface, I would like to say that other optimizers exist, but I will only be covering momentum in this video. So what is the problem with vanilla gradient descent? So loss functions are infamously non-convex. They have little local maximums and little local minimums all over the place, and this might fool the gradient descent algorithm into converging at a non-optimal local minimum, even if a more optimal minimum is close by. For example, in this diagram, it might be fooled into believing that this little dip in the loss function is the most optimal local minimum, when it's actually here, denoted by this asterisk. So momentum solves this problem by taking past velocities into account, or past tweaks, in other words. This technique makes it harder for temporary dips like this in the loss function to be confused with the actual most optimal local minimum. Additionally, momentum-based gradient descent always, or almost always, converges much faster than just vanilla gradient descent does. What momentum-based gradient descent is essentially an approximation of Hessian-based gradient descent. If you aren't familiar, a Hessian matrix is similar to a gradient vector, but instead of it containing all of the partial derivatives of the loss function, it's a square matrix that contains all of the second-order partial derivatives. And what that does is it doesn't only tell us the rate at which the loss function is changing, but it's also telling us the rate at which the change in the loss function is changing, the slope of the slope, if you will. It's essentially doing the same thing, except Hessian-based gradient descent is very inefficient, as it would require you to compute significantly more values. If you were to have, say, 10 weights, instead of computing just the 10 partial derivatives with respect to each weight, you actually have to compute 100 second-order partial derivatives, 10 to the power of 2. And that's extremely inefficient. That's why we resort to using momentum optimizers as opposed to Hessian-based gradient descent. So a common analogy to gradient descent is a ball rolling down a hill. And I think this is not only a common analogy, but it's a decent analogy, especially for someone who's trying to visualize what gradient descent actually is like. The problem is that a point in space doesn't have mass like a ball does. So you can't simply use the standard momentum equation, mass times velocity, because there is no mass. So the question now arises, how do we actually work around this? So instead of using mass to calculate momentum, we use history, or rather the history of past tweaks or past velocities, past changes, if you will, as it descends. So you can use like a fixed Q data structure to store, say, the past 5 tweaks during the gradient descent process, and that's what you would use to calculate that momentum factor. So how is it done? As you can see, this is going to be our tweak history. Gamma is our momentum constant. It's usually a value between 0 and 1, and a common value that people use is 0.9. L is our learning rate, nabla represents our gradient vector, and C is our loss function. So I'm sure you're familiar with just the vanilla update equation. Your new weight is equal to the current weight minus the learning rate multiplied by the gradient, or in other words, the partial derivative of the loss function with respect to that weight. Now, if you want to have the same thing but apply momentum to it, it's the same update equation, except this time we are adding our momentum constant multiplied by the last tweak. What you can actually do, instead of just taking into account the last tweak, is you can also take into account the past k tweaks. So maybe the last 5 tweaks if you wanted to. And all you have to do is sum up those past tweaks and multiply it all by the momentum constant. There is only one problem with this, however, and it's that tweaks that were made way back in the beginning are going to hold way less importance determining what the current momentum should be than, say, the last tweak is. So what we can actually do is, instead of multiplying all the past tweaks by the same momentum constant, we can actually reduce the momentum constant by raising it to a power 1 greater than before. So as you can see here, the momentum constant that's being multiplied by this tweak is going to be 0.9 squared, which is 0.81. And here it's going to be 0.9 cubed, and then 0.9 to the power of 4, 0.9 to the power of 5, assuming that we're taking into account the past 5 tweaks. And this is what that modified update equation would look like. Instead of having gamma be multiplied by all of the tweaks added together, we are going to raise it to the power of the indexer of the summation and multiply it by each tweak independently. So here's an example of that in action with some actual numbers. This is our tweak history for our past 4 tweaks. We are going to keep the same value for our momentum constant, and all we're doing is this is just the vanilla gradient descent update equation, but we're adding it by gamma times the last tweak plus gamma squared times the tweak before that, plus gamma cubed multiplied by the tweak before that, and so on. And that turns out to be 0.6815. So hopefully this gives you a good intuition of how momentum optimization works, and hopefully you can apply this to your future projects. If you're using vanilla gradient descent and it's just not working for you, and it's not converging either fast enough or it's converging at some non-optimal local minimum, you might want to consider using momentum. So thanks for watching, and I'll see you in the next one. Goodbye.